Imagine you have a square piece of rubber sheet drawn on paper. Now imagine you apply some kind of stretching, squashing, rotating or shearing force to the whole sheet. This force is what mathematicians call a linear transformation. After this force is applied, most arrows, directions, that you drew on the sheet will change both length and direction. They get twisted around. But surprisingly, there are always a few very special directions that behave differently. These special directions only stretch longer, shrink shorter, or sometimes flip 180 degrees, but they never turn left or right. They stay pointing exactly along the same line as before. These magic unchanged directions are called eigenvectors. The German word Eigen means own or characteristic. So eigenvectors are the characteristic or natural directions of that stretching force. For each eigenvector, each special direction, there is a number that tells us exactly how much stretching or shrinking happened along that direction. That number is called the eigenvalue. If the eigenvalue is 3, the arrow becomes 3 times longer. If it is 0, 5, the arrow becomes half as long. If it is 1, nothing changes in length. If it is 2, the arrow becomes twice as long, but points in the completely opposite direction. It flips. If the eigenvalue is 0, the arrow gets squashed to a single point. That direction completely disappears under this transformation. So eigenvalue tells how much, and eigenvector tells in which direction the simplest action happens. Why do these two things matter so much in real life? Because most complicated movements and changes in the world, whether it's vibrating guitar strings, spinning airplane wings, heat flowing through metal population changes in biology, or how light reflects in computer graphics, can be described by big matrices, grids of numbers. When we find the eigenvalues and eigenvectors of those matrices, suddenly the complicated mess becomes very simple. Instead of dealing with hundreds of connected equations, we can break the problem into independent directions, the eigenvectors, and just multiply by simple numbers, the eigenvalues, in each direction. This diagonalization trick makes hard calculations easy, fast, and stable. Here are just a few cool real-world uses. Google's original PageRank algorithm finds the most important web pages using the principal eigenvector of a giant internet link matrix. In face recognition apps and image compression, like JPEG, eigenvectors help find the most important patterns in faces or pictures. In machine learning and neural networks, eigenvalues tell us whether the training is stable or will explode. In physics and engineering, eigenvalues give the natural vibration frequencies of bridges, buildings, rockets, and molecules, helping engineers make sure nothing shakes itself apart. Even quantum mechanics uses them to find energy levels of atoms.